Okay. So we use economic model, right, to describe economic activities, but of course at the abstract level of reality. Why we say abstract? Because we have a lot of assumptions that we make, right? But what is more important is most of these models has been, tested or tried to be proved proved by uh, the previous economists, right? So it's basically just um, something that we use to understand the simple relationship between two variables, for example. And that's why we have the assumption of ceteris paribus, where we hold other things constant, because we mainly want to highlight only some of the important variables. And econometric will help us in, in looking at or how to control for other variables in our estimations, empirical estimation. Now, since the models involve a lot of assumptions, then people would, like I say, have they are always skeptical about economics, but we or any other models other than economics should have a method, right, to verify the models. So there are two ways of verifying models. The first one is direct approach. Second one is indirect approach. So direct approach is a bit more theoretical, I would say, in manner, because we have the assumptions. So we have to basically validate the model's assumptions, right? But there's an indirect approach where we can basically shows that the model basically correctly predicts the real events. For example, in economics, we say that if price increase, that's the simplest and also the most basic relationship that we learn from Micro 101 until our undergraduate, postgraduate level. Even if you go PhD or postdoctoral, that relationship won't change, right? That is, if your price increase, then the quantity demanded will decrease, right? So what we can do to basically verify that model, as demand model, is basically to show that that relationship holds, and it's basically predicts the real world by if you're taking data from the ground and then estimate the demand function, and then that relationship holds. All right. Of course, it's sometimes it's not if it's given good, for example, right? But most of the time we see that um, that relationship basically is true, lah, right? Now, the general features of economic models, like I said just now, is ceteris paribus assumption, that is holding other things constant. We want to examine the relationship between X and Y, for example, right? And that is also in line with the econometrics estimation, right? Where if we have estimate, right, a function, then the beta, right, the coefficient for one independent variable would basically be the marginal effect of that independent variable on the dependent variable, holding other variables constant, other variables that we have in our estimation. Okay, and also another feature of economic model is the assumption of optimization behavior, right, of individuals. And that means we have an objective function, and the whoever the economic agents that we trying to analyze in the behavior, we want to optimize that objective function. So optimize means it can be minimizing, it can be maximizing, right? So we're talking about normally in microeconomics, we're looking at the maximization of utility, right, or maximization of profit. And of course, we have the dual problem of that is minimizing the budget as well as minimizing the cost if we are looking at firms, right? So given this optimization assumption and the flexibility in terms of what are the determination of the objective function that allows us to study or apply the same basic economic models to understand other behaviors. For example, how criminal behave, and then how a government behave, something like that, right? So as long as we can set the objective functions of these economic agents. And also we made distinction between positive and normative kind of analysis or statement, right? I think this is also most basic things that we learn from undergraduate economics. That is, if you are looking at, for example, some sort of like a relationship between variables, right? That means we're looking at something, positive. That is, we say that um, one increase will lead to the other one increase, for example, right? So normative is much more on value judgment, okay, rather than something that is more objective. Right, but of course, we have both components, right? The objective, uh, what you call that, statement, as well as the more value judgment things. Okay. And so the examples given here, like in economic model, you have basically in microeconomics, going to look at household and firm. So the objective function is to the utility function, and the optimization behavior is to maximize the utility, and for firm to maximize profit, right? And there are endogenous and exogenous variables, where endogenous variables are something that you normally what we want is find, right? If you're talking about the differentiation, so this is the one that we want to differentiate the function with respect to this endogenous variable, right? Which is within the control of the economic agent, right? But there are also exogenous variables that is taken as it is. So in the case of uh, households, it's the price of goods, and the case of firms, it's the price of inputs and also outputs, right? So but of course, we are still also interested in looking at how the exogenous change in exogenous variables, right, will affect the objective optimality, ataupun the utility level, the maximum utility level of the households, and also the maximum utility level of the profit level of the firm, right? That is also going to be one of the important analysis that we will also look at when we look at consumer and also producer problem. Hold on. That's a challenge when you do your class at home. Hold on, eh? Right. Now, sorry for that. Now we look at the what do you call that? The applications of economics. So there are some, and I believe most of us here, in the area of applied economics, right? So we have this, definition of applied economics, which is an application of economic theory and statistics combined with the knowledge of institutions to explain the behavior of real world phenomenon. So we have, like I said just now, the economic theory, right? And we have the observation on what happened in the real world. So we have the theoretical abstraction, which is all the economic models that we're going to go through, right? And then we create hypotheses out of that. And of course, in if you're talking about statistics and econometrics, then we have our empirical testing to show that uh, to prove the theory, and then we have the interpretation of the empirical findings, and that should be actually in line with the theory that we have, the underlying theory that we have, right, to explain the real what happened in the real world, right? Uh, so in the Oopsie. All right. Now let's look at the some of the mathematical tools that we use, right, for microeconomics. Now we start with maximization of a function with one variable. I know for some of you, it might be something that you have learned at your undergraduate level, right? But we're going to go through one variable, which is the most simplest one, and then several variables, and also the maximization of function with the constraint optimize what do you call it, with the constraint, so that we're looking at constraint optimization problem, right? So in looking at the behavior of agents, right? Like I said, the features of economic model that we have just now is that we're always going to assume that the agent will want to optimal some objective function, right? Some optimal time trying to find the optimal value of some function, right? And which we call objective function. And that normally we have this, consumer maximization, and also firm seeks to maximize utility, consumer seek to maximize, firm seek to maximize profit, and consumer seeks to maximize utility, right? Um, and we have the first order condition. So this is from the mathematical economics. If you're taking it right now, you might be seeing almost the same thing, right? And it will be useful as well, right? To uh, if you're taking my mathematics and also advanced micro and advanced macro at the same time. So the first order condition for a maximum is we have the objective function here, pi or f, right? Whatever that function that we have. Then the differentiation of the function um, must be equals to zero, right? That is here the function of one variable to attain its maximum value at some point. So the derivative at that point must be zero. All right, so that's the first order condition for maximum. And then we have the sufficient condition as well for a function or a value to be at a maximum level, right? That is referring to the second order conditions here. Okay. But most of the time, when we have already looked into the consumer theory and producer theory, we rarely use this one, right? At least for this course, but of course, we have at the back of our mind that the second order conditions also holds. That is the sufficient condition here. So it's only a necessary condition for the first derivative ataupun the differentiation to be equals to zero. That is only to let us know what is a critical point, right? And then we have the sufficient condition, because an optimization optimal point here can be maximum or minimum point, and then that will be determined by the second order condition. Okay, so these are the most basic mathematical conditions that we learn from our undergraduate mathematical economics, right? Um, yeah, so it's required for if the second order condition to be negative, right? So it's going to be that means the point that we have, the critical point that we solve when we have the first order condition equals to zero, is going to be the maximum point for the objective function, right? So that means the 2 pi dq square here, right? Less than zero. So we are looking at that actually fulfill the sufficient condition that the critical point that we found here is a maximum point. Okay. And there are important rules of for finding derivatives. Um, so the most common one is if it's constant, then the derivative of a with respect to x will be zero. And if a in this case, we have the functions of the function with argument x, right? And a is a constant there. Then when we take the derivative of this function with respect to x, then the what we call that the results would be as such, a f prime x, right? And so on lah, right? So we have log function. We have the if ax is actually a power of something constant or something function, right? Then we have all these rules telling us what will be the results of the first derivative, right? And if you have uh, the basically two components, I would say, in our function, but both is a function of x here, right? So that means let's say that this is x plus 2x, right? So we can basically get the the derivative by um, differentiating the functions portion by portion, ataupun part by part, right? So this is if this is x, for example, right? And then x 2x as now. So we can basically wait, hold on, right? So if it's um y is x plus 2x, right? I think you know the rules. So dy dx going to be just portion by portion. So 1 and 2 here. Okay. And then if it's a multiplication of two components, um, normally we have, for example, let's take an example x and y, lah, for example, right? Or maybe like a certain, maybe something like x squared plus 2 times 2x. I just made this up, right? Something like that. So then we have this rule, quotient rule, right? Where the derivative of this function will be as such, fx g prime x plus f prime x gx, right? So if you have here has fx and this second part as gx, right? So it's going to be x2 x squared, for example, plus 2, then times g prime x is 2, right? And then plus the other part of it. Okay, that is f prime x gx. Right? So f prime x is 2x, times 2x plus 1. Okay, so I think hope you still remember this. And also we have if the function is the this one is multiplication and this one is 1 divided by the other, right? And then this is the rule following this kind of function, right? So instead of multiply, let's say x2 plus 2 divided by 2x plus 1. Okay, something like that. Okay, so follow this rule in order for us to find the derivative. And if you have implicit function means that in this case, we have indirect relationship between y and z, right? And then that's through x. So we have the y actually as a function of x and x is a function of z. And we are interested to find what is the relationship and how basically z will influence y, right? But that influence is basically through x, all right? So we have that, what do you call that, derivation of y with respect to z, that is trying to find out what is the impact of z, changing z on y. But that relationship basically comes from come through x basically, right? Okay, so we take the differentiation of y with respect to x and then x with respect to z. Right, and then we have functions of several variables. Normally we're going to deal with this kind of function. And if you are, familiar with consumer optimization or a firm's cost minimization or profit maximization, then we're normally going to see utility as a function of two variables, x1, x2 at least, right? Or production as a function of, well, let's say, labor and capital, right? Labor and capital. Okay, or we can put it as x1, x2 as well, but we can normally understand that the in the production function, it relies on labor and also capital. Okay, so most of the time we're going to deal with functions with more than one variable, but the derivatives won't be that much different, I would say, because we're still going to be using these rules. But of course, because we have two variables, then we have a partial derivatives. That means that when we take a differentiation of our function with respect to one variable, then we are basically holding other variables constant. So we're basically treating the other variable as a, a here in this case is a constant, right? And then that's how we're going to treat the other variables here if we're talking about x, y, or x1, x2. All right. So taking differentiation of y with respect to x1, that means we hold x2 as a constant in that process. Right. And these are all the what do you call that? The examples, I would say, of calculating partial derivatives. So, for example, here we have y is a function of x and x1 and x2, and then it takes a specific function of a x1 square plus b1 x1 x2 and c x1 square. Right? So we take the differentiation with respect to x1. So remember that we treat x2 as constant in that process. So we have 2x ax1 from the first part of this function, right? And then we have b since we have x2 here and treat x1 and sorry x1 here and treat x2 as constant. So we left with bx2, and that is coming from here. And then since there's no x1 in this part of the function, then this just become constant, and anything that uh, constant will just become zero. Then if we take the partial, or if we take the derivative of a constant with respect to x, right? So that's this term drops out from the first derivative, or the partial derivative with respect to x1. And similarly, if we are looking at x2, so we take x1 as what do you call that, as constant. So in this case, in this term, there's no x2. So all of this uh, part become, or term here become constant. So it drops out. And what left is these two terms coming from the second and third terms from the functions that we're trying to find the partial derivatives, right? And the rest follows. This is similar to the derivative with one variables. The only difference is that now we have two variables, right? So in this case, if we have an exponential variable here, e, and then we have a power of ax1 plus bx2, then remember that the way we derive this is, the way we find the, what do you call that, the derivation of this is if it's a function of x, then the derivation is going to be e as still a power of fx and then f prime x, right? Okay, so we might see some of these functions later, either as normally as a utility function, right? So in this case, we have e to the power of ax1 plus bx2. So then we just take the whole function here, right? E ax1 bx2. And then we a coming from is coming from this one, this part where we differentiate the power itself with respect to x1 in this case. If, so this one, x1, x2, 1, x2, and this is f1. Okay. And similarly here lah. So that means this is e still x1, x2, and then f prime 2 lah, if you are to represent the differentiation with respect to x2. Okay, so the rest follows, like this one, x1, x2. So again, anything log, then the constant would, the times 1 over x1, and in this case, the constant times 1 over x2. So that's how we get the partial derivatives of this function. Right? So we are particularly interested in, if you're talking about the partial derivative, right? We're looking at the effect of changes of one variable holding other variable constant, right? So that is the ceteris paribus assumption that we have earlier on, which is not there when we are looking at the single variable, of course, because we are looking at only one variable affecting the other, right? So the ceteris paribus assumption is particularly important when we are looking at the functions with several variables. Okay, and it shows changes in one variable, and how it's actually affect the objective function, right? By holding other factors for other variables constant, right? And we have, of course, the second order partial derivative that is taking the partial derivative of partial derivative. So we have the partial derivative of f with respect to x1, and then take another partial derivative of this first partial derivative with respect to xj, for example, right? So we have fij in this case, all right? So it tells us if this is a marginal effect, right, of xi on f, then if we take the other partial derivative, then it will tell us basically whether the effect is increasing or decreasing. Uh, the effect of change in xi, for example, if we're taking sorry, f11 in this case, right? It's just telling us well, what is the marginal effect of a marginal effect, right? Something like we have, for example, we have the diminishing marginal returns or diminishing marginal utility. So how do we basically show that is by taking the second order partial derivative and show that if it's negative, then that assumption of diminishing marginal utility or diminishing marginal productivity, for example, it's whole. And it's also important if we want to do some theoretical work, or if basically we're dealing with mathematical modeling, when we do research, yeah, the two kinds of what we call that study normally, right, in economics. So one is basically purely based on using mathematical functions, and so it must, whatever function that we use, it must basically uh, be in line with the assumptions that we have in economics, right? So it must take into consideration, for example, if you're presenting utility with utility function, and then it must basically have all the fulfill all the characteristics of a utility functions, the assumptions that we have, right? Okay. And then we have Jung's theorem related to the second partial derivative. That is, under general conditions, the order in which partial differentiation is conducted to evaluate second order partial derivative does not matter, right? So if we take the derivative of x one first, then with xi first, then followed by xj, then it will just give us the same result as if we take the derivative of xj first, then xi. Sorry. All right. So that's basically based on Jung's theorem. And then right, so this is what I've talked about just now, right? The second order partial derivative basically play an important role in many economic theory because we have all of these assumptions of diminishing marginals, and that's how we show it, right? How we show that it's the assumptions of diminishing marginals by showing that the second order partial derivative, for example, in this case, in many cases, because we see that we have most of the time diminishing marginal, right? Then uh, if you're taking the difference, second partial differentiation, right, with respect to the same variables, and it's negative, so it's actually indicating a diminishing marginal effectiveness. Right? So effectiveness here is referring to how xi in this case is influencing the value of y. Okay. Hmm. Right. So that is the rule of second partial derivative, and it's not only that, right? Because in functions of several variables, we also have in finding the optimized level, optimized value, then we still have the um, necessary condition and also sufficient condition, right? So similar to this, the single variable function, in which we have to use the first order condition and also second order conditions, right? But of course, everything that we do here have some economic meanings, right? So that we would appreciate when we look at all the mathematical models presented in the journal articles, right? So we know that why certain assumptions is made, why some variables or the derivative, for example, is assumed to be negative, and then the second partial derivative is assumed to be negative. So there are always going to be some relations to the economic theory, right? Now, the maximization of function of several variables. So suppose that we have an agent who wishes to maximize the y, right? And then that y is a function of x1, x2 until xn, right? And then the first order conditions for a maximum, that is a necessary condition for maximum, is to have all the first partial derivative to be equals to zero. So that means we have systems of equations, right? Because we have more than one variables. So it'll be direct if we have only a single variable. So take the differentiation of f or y with respect to x, and then equate it to zero, and then we can solve for the value of x that will maximize the objective function, right? But in this case, since we have more than one variables, so we have all of the first partial derivative to be equals to zero. So this is similarly of writing down all of the first order conditions to be equals to zero. Right, so if you have n, what do you call that, n variables, right, choice variables. So we have n variables to solve and also n number of functions here, right, to be used in order to solve for n unknowns. So we have this, the rules that we have should have a similar number of functions to solve if we have a certain number of unknowns, right? Okay, but again, it's not a sufficient condition. It's only necessary condition for optimization. But if you're seeking for maximization of the function, then it must fulfill the second order conditions as well. Okay, right. Second order partial derivative must be negative, and that is the condition for the sufficient condition for optimization of a function with more than one variable. Um, and most of the time, we're also going to use envelope theorem, right? So envelope theorem is basically, if you still remember that we have the exogenous and endogenous variable when we look at the example of economic model just now. So basically, envelope theorem is used to understand how changes in the exogenous variable affect the objective function, ataupun the functions that we are trying to maximize, right? Utility, for example. So we have normally a situation where um, we were we're trying to find what is the combination of x1 and x2 that will maximize the utility of the individual, right? So I can consume 1x, 1, 2, 1x1, 2x2, or any other combination of x1 and x2 based on specific utility function that I have. And do all these partial derivative, equate it to zero, and then prove it that is maximum. But there are also sometimes, right, we want to know what is the impact of change in, let's say, price, even though there's no price here yet. In particular, if we are going to look at an economic problem, normally it's a constraint optimization where price will come in from the budget, right? Then we want to look at the impact of change in price on the objective function, and then that is where the envelope theorem will become handy, right, for us to use. right? Otherwise, we will have to solve the optimization problem one by one. That means if we change A, then for example to A prime or A1, then we do the optimization, solve for the optimization problem. And then if you want to look at the impact of change in A, for example, to A2, then we do another, we have to do another optimization by just changing A, because remember A here is constant, right? So if you do the optimization and the first order condition is going to give us dy dx, so you know the impact of x on y, right? But now we are interested in looking at the impact of A on y rather than x on y, right? So one way to do that is to change A every time, right? So you can have two. For example, specifically, if you say y is negative x squared plus, let's say 2a, right? And then we do the optimization and say that, or we want to look at what happened if a increase to 4a, for example, right? Then we're going to have to find the first order conditions again, right? In order for us to find what is the impact then on what. Okay. But we can basically have, or basically can utilize what we call envelope theorem in order for us to, sorry, not A, this is X. Okay. Um, to look at the impact of a parameter here, right, on Y, right? So basically by, if you're using envelope theorem, right, it is by taking the differentiation of the optimized function with respect to the parameter, or in this case A, right? So a small change in A can be computed by holding X at X star. So X star is the optimal value of X, that is value that maximizes the objective function, right? And calculating dy dA directly from the derivative of y with respect to it, right? But what is important is to hold x at its optimal value, right? Because in this case, we say that we already have what is the optimal y, right? And then that given, what is the value of x that maximize the value of y. But then after that, then we can analyze what happened to y when a change, right? That can only be evaluated when the value of x is already, uh, you know, already uh, give the, or already derive the maximum value of y, the optimal value of y. Okay, so that the YDA is evaluated at the point where x is optimal, right? And in this case, this is comparing the two approaches here. The first one is to solve, in a, it's not a long way because it's just a simple equation that we have here, right? A simple function that we have here, right? So dy dx, first to derive the optimal value, that give us the value of x star at a divided by 2, or a over 2, right? And then substitute that back into the y function, right? So we have y just now as a function of negative x2 plus ax, right? Yep. Okay. So once we get the x value here, substitute that back into the objective function so that we have the optimal y, right? And then differentiate this with respect to a in order for us to find what will happen to, or the relationship between A and Y, right? Okay. So we know that now if we increase by 1, then the impact is actually half. Y will increase by 1/2. But using envelope theorem, we can basically, what we can do is to differentiate directly Y with respect to A. So in this case, dy dA is X, and evaluate this X at X star. Okay, so X star here is A/2. So dy dA is basically A/2. Okay, so it's basically giving us a similar outcome, but of course, we get the result faster, right? In this case. Okay. And like I said, it's maybe look insignificant, right? When we're looking at a simple functions like this, but this will be helpful when you're looking at, for example, constraint optimization or function with which is much more complex than this one. Okay, so we are going to use in envelope theorem in some of the analysis that we're going to have later on. Uh, so the envelope theorem basically is looking at the change in the optimal value of a function with respect to a parameter of a function that can be found by partially differentiating the objective function while holding x or several x's if you're looking at a function with several choice variables, right? And holding that at its optimal value, just like the one that we did here. Okay, we're taking differentiation with respect to A and then evaluate that at the optimal value of X. Okay, if there are any question before we continue. Oh, okay, I should stop right now. So sorry about that. Someone should remind me. It's already time for breaking the fast. So we'll take a break right now and for 30 minutes, right? For um some of our Muslim friends to break their fast, and then we pray Maghrib and then we'll come back later on. All right. So I'll entertain your questions after the break. Thank you so much.